Hello, everybody. So we're going to start lecture today by taking a look at these examples we left in class on Monday, which were examples of SN1, SN2, E1, and E2 reactions. So basically, that's the question we're going to ask for each of these is which mechanism do we think will be the dominant mechanism, and then we'll predict the major product from that mechanism that we come up with. Okay, so let's start with this first example. So again, remember that the most important factor, and this is where we should start for each one of these examples, is the identity of the electrophile, or in this case, it'll be the alkyl halide. Okay, so we're looking at that bromide. Okay, so this first example is a primary bromide. Okay, and so now what we want to think about is, what reaction, preferred an unhindered electrophile. So remember, there's only one reaction that preferred an unhindered electrophile, and that was SN2. So remember that E1 and SN1 and E2 all preferred a more substituted electrophile. Okay, so we can be pretty confident in our assignment of SN2 from the electrophile alone. The only times we would get any other reaction besides SN2 is if we had a bulky base with a primary halide, or if we had a really weak nucleophile. That might be an example where we wouldn't observe a reaction. Okay, so if we're going to, follow the premise that we're undergoing an SN2 reaction, we need to make sure we have a strong nucleophile. Okay, so that oxygen anion is in fact a strong nucleophile. It's also a strong base, but that's irrelevant if we're thinking about a substitution reaction. And then what about DMSO? So DMSO was an example of our polar aprotic solvent. So all of those things together lead us to the assignment of an SN2 reaction. Okay, so if you wanted to think about the mechanism of SN2, remember it's a concerted single-step mechanism. Okay, that happens through backside attack, although we don't have a chiral center here, so we're not going to have to worry about it in this particular case. Okay, so this was an example actually of Williamson ether synthesis, and we might have actually looked at this specific example before that gave us a similar product. Okay, so let's go ahead to the next example. So the next example, we have a tertiary halide. All right, and so basically we can eliminate SN2 as a possibility here. So we're either going to have an SN1E1 or we're going to have an E2 reaction. So then we'll go to the reagents and conditions, and we see methanol there. Okay, methanol being the only reagent there. It's also the solvent. That gives us a pretty good idea that this is going to be a solvolysis reaction. Okay, so just a few things about methanol to remember is that as it's a neutral oxygen, it's a weak nucleophile, weak base. So remember that, the strong nucleophile, strong base favor the 2's mechanism, SN2 and E2. Weak nucleophiles, weak bases promote the 1's mechanism, SN1 and E1. Okay, so something else about methanol. Yes, it's a weak nucleophile and a weak base. It is also a polar protic solvent. Okay, and so for all of those reasons, we're going to predict an SN1E1 reaction. Okay, so for SN1, we're going to do the substitution. If we had a chiral center, we would generate a racemic mixture. In this particular case, we don't. So there's the SN1 product. And then remember that the E1 product is going to follow Zaitsev's rule. So we're going to put the alkene at the most substituted position. And so we would get this mixture of substitution and elimination products, SN1 and E1. Okay. So the next example, we actually have the same exact starting material, so still a tertiary halide, and then we need to go over to LDA. And you might have a solvent here, so THF might be an example of a solvent you could see here. But one thing that we need to remember about LDA is we talked about something very specific for LDA, and that was that it was a bulky base. Okay, so what reactions do bulky bases promote? So they promote the E2 reaction. So remember, another name for a bulky base is a non-nucleophilic base. So if it's non-nucleophilic, it cannot undergo an SN2 reaction. Okay, and it's not going to undergo an E1 SN1 reaction because it's a strong base. Okay, so bulky bases give E2, and there was something special about them. Remember that they altered the regiochemistry to give us the Hofmann product, or the less substituted alkene. Okay, so you could form the Hofmann product at either one of those methyl groups as the beta position. Those will be equivalent products here. So I'm going to go ahead and put my alkene out there. So again, you could have put your alkene at that position. That would have been the same product. Okay, so again, LDA bulky base is going to promote E2 regardless of if we have primary, secondary, or tertiary alkyl halide. Okay, so let's go to the next example. So here's one of our tricky examples, right? So we have a secondary halide. And so really any reaction is fair game with a secondary halide. And so then we're really going to lean on the reagents and conditions to figure out which reaction is going to operate here. Okay, so we've seen this sodium ethoxide earlier in our examples. So it's a strong nucleophile, but it's also a strong base. It's one of those that has a conjugate acid with a pKa greater than 11. The conjugate acid is ethanol, that pKa is around 15. And so it would be strong enough of a base to promote an elimination, E2 reaction. Okay, so what else is gonna tell us that this, are clues telling us that this is an E2 elimination? Well, one is the solvent. So the solvent is polar protic. Okay, so remember that very typical E2 conditions would be our strong, oh, I realized I forgot a word here, would be our strong base in its corresponding conjugate acid as the solvent. So let me just fix that. So strong nucleophile, strong base. Okay, so it's very typical for E2 to have that, ethoxide in ethanol as conditions. And then remember that heat promotes elimination reactions, as we mentioned in class on Monday. Okay, so all of this tells us that it's going to be an E2 elimination. And so if we're looking at this starting material, we have two beta positions, right? So we have beta 1 and beta 2. Remember that we need a hydrogen that is capable of being anion coplanar to the leaving group at the beta position. So notice at beta 1, although that would give us the more substituted alkene in theory, there's no hydrogen there, right? So I couldn't form an alkene there because I would overexceed the octet at that carbon. Okay, so then we're going to take the proton from beta 2 position and we'll end up with this alkene. Okay, so there's our E2 elimination product. Okay, so next we have an example with a secondary halide. Okay, so this bromide, and now we have this tert butoxide and T-butanol. All right, so tert butoxide was another example of a bulky base, and notice how we're in that conjugate acid solvent T-butanol. So bulky bases, non-nucleophilic bases, they undergo E2 reactions, and as we saw earlier, that's going to give us the Hofmann product. Okay, so let's go ahead and label our alpha and beta positions up here so we can think about which proton we're going to remove. So in order to get the Hofmann product from this starting material that we're looking at, would I want to remove a hydrogen at the beta 1 or at the beta 2 position? Oh, these both say 1. Okay, so at the beta 1 or the beta 2 position. Okay, so I would want to remove it at the beta 2 position. So remember that bulky bases remove the beta hydrogen at the most sterically accessible or the least sterically hindered position. And so for that reason, we would eliminate to make this terminal alkene. Okay, and then lastly, I say I did another one of these bulky base things, so I'll come up with one more example here before we move on. Okay, so here we have our tertiary halide with a bulky base. So again, more of the same. We're gonna see an E2 reaction favoring the Hofmann product. Okay, and so then the Hofmann product would be this. All right, and in this case, I actually had 3 beta positions, so beta 1, beta 2, and beta 3. Notice how beta 1 and beta 2 are equivalent, and then beta 3 is unique, and that's the least hindered position, and so that would give us the Hofmann product. Okay, so let's do one last example just to make sure that we can, see something other than a bulky base. So let's go ahead and do this starting material. Okay, so we're going to take this sulfur anion, the sulfide, and we're going to react it with, let's do DMF. That was one of our polar aprotic solvents. Okay, so here I have a secondary halide, which could go by any of the reactions. So sulfur anions, those are strong nucleophiles, but they're not particularly strong bases. The pKa of their conjugate acid is less than 11. And so we would expect this then, especially coupled with this polar aprotic solvent, to lead us to an SN2 reaction. Okay, so remember that SN2 goes by inversion of configuration, and so we can see that the incoming nucleophile, that sulfur anion, will come in from the backside and displace our bromide. Okay? All right, so hopefully going through these examples, gave us an idea of, how to approach these problems. I would definitely recommend going to the workbook problems, the textbook problems, or even just typing in, SN1 versus SN2 reactions on Google. There was also that backside attack game that I told you about at the end of lecture last time, which was an iPad, iPhone app that you could download to play. Okay, so I'm gonna stop this recording and make this part 1. When I come back in a few minutes for part 2, we are gonna go ahead and start chapter 10. So some things that you're gonna need to start chapter 10, obviously we'll be taking regular notes, but also we're going to talk about nomenclature of alcohol, so you'll wanna get your nomenclature packet out. Okay, I'll be back in a few minutes.